Welcome to the Tell Me series, a new podcast series with the goal to look outside our bubbles and rekindle our childlike curiosity about the world. This podcast is not, I repeat, not about productivity, career, or life hacks. It is purely about seeking discomfort by learning a little bit more about our world every week. Today, we will delve into the world of mathematics, astrophysics, and my favorite, music. What do math and music have in common? Are most musicians good at math? And if so, why? How are discoveries made in each field? All of these are explored on today's episode of the Tell Me series. To inaugurate the first episode, I am super excited to have on the show one of my best friends, Varun Kumar. Varun and I were in the same band in high school. I often think of our relationship much like that of Phineas and Ferb. I tend to be more of a Phineas, the optimist, the playful explorer, while Varun is more of a Ferb. Let's just say he's a man of action that tends to keep me grounded in reality. He is currently in Germany, pursuing his second master's. That's right, his second. His first was in astrophysics from the University of Glasgow, and the second is in mathematics from the Darmstadt University of Technology. Varun, welcome to the show.
Hey man, thanks for having me. That was a very nice introduction. Thank you very much.
Awesome. So, Varun, you've been quite involved with math from a young age. Most people are quite the opposite. They're glad to let go of it right after high school. When did you first realize you were enjoying math?
So I would say probably even when, quite young, when we were in maybe grade 2 or 3, maths at that time had quite a problem-solving component I enjoyed. It was just, calculations, and you were just testing your skills in terms of, yeah. And I really enjoyed that aspect, and you would get, more challenging questions that you could try and fit different skills together, and I really enjoyed that. Yeah, and we as we got older and we went to high school, that only evolved. We learned new subjects, but the essential component of trying to problem solve, trying to fit different things together, whether that was geometry and algebra or anything else. I really enjoyed that aspect of maths in school, and I think that isn't emphasized enough, maybe.
Why do you think most people don't connect with math? Do you think it's something perhaps you experienced in your childhood that they might have missed out during their formative years?
I think it could be a few different things. I think I happen to be maybe someone who is the kind of maybe intelligence I have is the kind that is tested in school. So I felt quite validated by the school system in terms of how well I was able to progress in the subject. I think for a lot of other people, they think and learn quite differently. So maybe maths that was taught with more reference to real world subjects, or that was taught maybe with reference to physics or science, would have a very significantly different impact, I think, and what other people might have enjoyed it a lot more that way, rather than just as abstract rules that you just then apply, which I enjoyed, but I understand why that maybe didn't connect so well with a lot of people.
Would you say you were influenced by some of your teachers? Like perhaps your math teacher was one of your favorites and that's what kind of got you into it?
Yeah, I was quite lucky to have good teachers, and my parents are both, so my mom did finance, my dad did engineering, so both of them quite mathematically oriented as well. But I also think for a lot of my maths classes, I will say that I think I spent a lot of time just head down doing the exercises on my own. And yeah, at that time, that was just something I really enjoyed. It's a bit like how at that age, many kids enjoyed doing sports and I didn't. I just enjoyed doing something that gave me marks and a good report card. So, but it was quite, in some ways it was quite self-driven, but I definitely didn't have any bad teachers, which I think is a big difference, that maybe a lot of people have had quite bad teachers that have sort of turned them away from the subject.
That's an interesting take. What would you say perhaps are some misconceptions people have about math? Perhaps not just about the subject itself, but maybe also about what you do in academia.
So I'd say maths is an interesting one because I think the way it's taught in school and the way most subjects are taught in school is quite separate. Everything is sort of placed in its own basket, and we don't tend to connect things. Maybe maths and physics a little bit, but you don't really investigate, for example, how people use geometry to make art. I mean, maybe we did that once in art class, but we never did it in maths class as like an actual mathematical subject, even though it is one of actual mathematical interest and research now. And so I guess that's exactly what I mean. I think people don't maybe know and are not taught really to appreciate how embedded maths is in a lot of different subjects and how useful it can be for exploring things you already enjoy. As for academia, academia maths has an entirely different flavor to everything we do in school, and it's almost like a completely different subject. I know friends who didn't like maths at school at all, and then when they went to uni, had a very different. They actually enjoyed the subject because it's so different. So academic maths, obviously, you don't know where you're going. And it's well known that in maths some problems are unsolvable. So any problem you tackle might actually not have an answer. And so that always adds an element of maybe fear, but also excitement, I guess.
Would you
Yeah,
say you're motivated by the side of excitement of the new possibilities of discovery, or are you more into having that structured thinking process?
I think it was very hard for me to leave what I'd grown to enjoy about school maths when I first came to uni because a lot of what I liked about school maths wasn't present in uni maths. Because, yeah, I mean, that thing of just constantly testing the same few skills in a very linear oriented manner of, we've taught you these exact, this skill of like solve the quadratic equation and now do 50 problems on solving the quadratic equation, and they gradually get harder. And that's just not really a thing. It sort of is in first year, but it sort of quite rapidly stops being how you do things, which makes sense. I think now I definitely, well, my favorite things in maths are sort of more wide than deep. I like to study subjects that maybe are connected to a few different areas of maths and maybe have some applications outside as well, rather than something that is very extremely abstract that is only relevant maybe to mathematicians now and for the next 200 years when someone might think of a use for it.
That's an interesting perspective. So tell me a bit about what you're studying at university right now. You mentioned offline that you're learning about quite of a new branch in math, and that your professor is close to being a founder of that branch.
Oh, yeah. We had talked about proof theory, I think. Yeah. So that's actually quite an interesting one. I think I've been trying to come up with a good analogy for this, but essentially proof theory it's not really a math subject, it's actually a logic subject, and those are considered separate areas. Um, and what I would say is that proof theory is a way of using logic to extract additional information from mathematics proofs. And I know that that sounds like a weird statement because I haven't placed it in any context. But what I mean is, say, for example, you and I are standing together in front of a house,
Okay.
and in the distance, we can see a supermarket. And I say to you, okay, Ronak, prove to me that you can stand in front of the supermarket. And you do the obvious thing. What do you do?
Just walk up to the supermarket
Yeah,
and stand there.
exactly. You walk up. But along the way, you walk and you actually count how many steps you take. So now, not only have you proved that you can stand in front of the supermarket, but you've additionally proved some quantitative information about how long it took to get there, or how many steps, or something like that. And that's the kind of, I mean, that's a very, very bad analogy, but that's what I mean. Applied proof theory, because it uses logic, which is a sort of underpinning of maths, in the same way maths is sort of an underpinning of physics, it, for free, gives us additional quantitative information from proofs that we have in a lot of different areas of maths.
So what would you
So,
say are like the practical applications of it that you've at least come across so far?
I mean, to a logician, practical applications are applications in maths. to anyone else, practical applications are applications in a real world subject like engineering. So it's difficult for me to say. I think the best thing that I would say are, so we traditionally, and my professor in particular, he's an analysis guy, and what that means is he from this subject he gets bounds or constraints on numbers. So for example, if I have an equation or I have a relationship and I want to put an upper limit on how far it can go, this logical process will reduce that upper limit without requiring any additional assumptions on the mathematical side. So we don't weaken our assumptions mathematically, but we get a stronger result.
I see. So are you basically saying that by adding that constraint, you're reducing the uncertainty?
Well, that's actually the point. In a sense, we're not adding constraints, and it's just adding additional insight into the original situation we already started with. So it's not that we're controlling an additional variable in the science manner, and it's just that we're saying we now have more surrounding data that tells us that this is actually going to be a lot less than whatever we can get just from this one thing. So that's kind of what's happening. And it is quite difficult to explain. And I don't really want... I thought about trying to do the whole... So the basic example we used was a proof of the fact that primes, there are an infinite number of prime numbers. And yeah, I mean, just for recollection, a prime number is obviously something that can only be divided by itself in 1. And there are a few different ways to prove this, but these different ways, for example, give rise to different constraints on the next prime. How far? So for any prime number I have, what's the distance between which I will definitely find the next prime?
Okay, so you're saying like between 2 and 3, there's 1, between 3 and 5, there's 2, etc., etc.
Yeah, exactly. And that is actually dependent on, obviously, the actual prime you're on. And so yeah. I mean, I think it's an interesting idea. I think I would like to see if I could, my personal thing, or what I would potentially be interested in for a thesis, for example, would be to see if I could apply this to algebra, because as far as I can see, this has been mostly an analysis or quite a numerical focus, which makes sense because it's about numerical constraints. But I would want to see if I could take it in that direction somehow.
Interesting. I've always been curious about how discoveries are made in both math and astrophysics. I remember reading recently that we detected gravitational waves for the first time, and that Einstein hypothesized that they existed through his equations. What exactly are gravitational waves, and how did Einstein discover them?
Okay, that's a pretty broad question. So let's maybe go through a little bit of... I don't want to take maybe the whole story, but Einstein's basic fundamental idea is... So we know that there are 4 forces, right? 4 forces in the universe. The electromagnetic force, the strong nuclear force, the weak nuclear force, and gravity. And Einstein's idea is that gravity is not actually a force, it's a trick. It's a trick of the surrounding space-time.
What does that mean?
Yeah, what does that mean? So it's basically how... So if I show you a map and I say, what's the shortest path from, I don't know, two cities that are on the same latitude, so the same horizontal line, the instinctive answer is to just draw a straight line between them. But that's not correct.
Is it because we're assuming that, I mean, a map is flat, but then the Earth is actually not flat?
The surface of the Earth is round, exactly. So the shortest line, also known as a geodesic in geometry and in physics, will look like an actual curved line, and it'll look longer than a flat line, but in actuality, that will be the shortest path.
I think I see where this is coming from. So is that the reason why, let's say if I was flying from here to the US, whenever you're in the plane, you see the map showing like you're going over Alaska
Yeah.
through
Yeah.
Greenland.
And it looks super
Interesting.
distorted because in your brain you're saying, well, there's a straight line. Why didn't we just go? But it's actually that the shortest path is, and it often is, of course, over the top of the world, which people don't really account for, and it's hard to account for on a flat map because the top of the world, which is a whole edge, is actually just one point.
That's right. We're so
So
used to thinking of maps and just space in general as something super flat.
yeah,
Whenever we think of Google Maps, when you open it up, it's just a flat map. You don't see quite the 3D image in your head.
yeah, you don't, and obviously that's a good enough approximation for the day to day, and that's fine. But so Riemann was a German mathematician in the 1800s, and he was he was not the first to start doing non-Euclidean geometry, but Riemannian geometry is essentially this geometry of curved spaces, and this is exactly what Einstein used, or how Einstein formulated relativity. He essentially said space-time actually gets bent and curved by mass. So something as big as a planet, or obviously something much bigger like a star or a giant black hole in a supermassive black hole in the middle of a galaxy, will obviously curve space-time quite a lot. And that's actually what gravity is. It's actually these distortions in space-time caused by mass. So it
So
is
is it
caused by
like,
mass.
if I had to explain it in a way that I might understand, is it something like if we have a trampoline and I drop like a heavy ball on it, you'll see a distortion because it won't be flat anymore, right?
Yeah, it's sort of like that. It's difficult to explain. I guess what a good analogy, yeah. What is maybe to take that analogy a little bit further, let's say you and I are standing and we hold this cloth or trampoline or something, trampoline material, and we've put a ball in the middle of it, a big, it's like maybe like a shot put, like something quite weighty in the middle. And so it's obviously weighted down. And then what you see is the orbit is maybe a marble, and it'll go around in a circle because of that distortion, and not because of some inherent, not like a rope between the two that it's like pulling, which is what we kind of think of gravity, but it's just an actual physical object that has just distorted the space around it. So then when the object is moving through space-time, as smoothly as possible, it's actually moving in this distorted space-time.
I see. So you would think that, let's say we have that shot put in the middle, but then I have a smaller, let's say a marble that I want to throw in, and you'd expect to throw it in a straight line to get, the shortest distance.
Yeah, exactly.
But then it turns
So
out when you turn it straight, because the shot put has curved, we use the topic of space time, it's technically curved our space. It will turn out to go in a path that is an orbital path.
yeah, so it'll look round to us, but to the marble, it'll be straight. It doesn't know that it's not moving in a straight line. It is moving in a straight line relative to its space-time. And this is the idea. What we call straight is fundamentally connected with the idea of flat space. But what we really mean is the most straight path that we could possibly take. And in a curved space-time, that is curved.
So then,
And
what
it looks
exactly is
curved
a
to us from the
gravitational
outside.
wave then? What exactly is a gravitational wave?
So, gravitational waves are, well, first of all, incredibly tiny, but also what they are is they're distortions in this space-time. They're sort of like quite small ripples, and they are, as I've said, quite incredibly tiny. They require like extremely sensitive instruments to measure and detect. I think currently we have 3 detectors that are actually capable of detecting them at the moment. 2 in the US, which are part of LIGO, and 1 in Europe, which is called Virgo.
I see. So, I mean, it seems kind of crazy to me that it's been almost 100 years since Einstein discovered them, and then we've only just begun to detect those waves. Why is it so hard to detect them?
Well, I mean, it's there's a few different problems with trying to detect them, really. So, first of all, when you actually calculate the waveform and you calculate the actual amplitude of these, you see that the distances that they're going to measure are extremely tiny. So that's one. And what you need then, the only things you can measure the gravitational waveforms from are essentially mergers of two objects that are already gravitationally strong in their own right. So, so for example, the first gravitational wave we measured in 2015 was a binary black hole merger. So
You're saying two black holes essentially just becoming one.
Yeah, well, it's not quite that simple because what happens is, as we just talked about, there's this distortion in space-time. So they don't approach like this. They do that, and this bit. So black holes individually won't really generate gravitational waves. And again, this is to do with the actual physical waveform. But this spinning of two of them actually does. And this is a very obviously powerful action, and yet it shows up on, I can't even remember the number, but it's a minuscule amount. And the other thing is why it's difficult to measure these is, so the minuscule amount is, I believe it's something like 10 to the minus 20 something of a meter.
Wow.
Yeah. That's not a lot. That's really not a lot. And so you need instruments that are A, very large, but also B, very precise, and then C, very resistant to outside noise. Because you build these instruments on the ground, and then any kind of seismic shock would produce something that was much more than that. And so how they're detected is also quite an interesting one, because you can't use a traditional ruler because the space-time that ruler is changing. So your ruler would stretch with the space you're trying to measure, and the only thing, and anything with mass would do this. And we only know of one thing that doesn't have mass, which is light.
What is that?
It's light. So we use lasers, and we have a sort of cross interferometer pattern that I really have no intention of getting into. But essentially, light isn't affected so much by these distortions because of the lack of mass. So we can use the lack of change of light relative to the change of space-time to measure the actual distortion, and therefore the actual gravitational wave amplitude.
Well, that's very interesting. And what would you say is the importance of having this detection? Like, why is it so important?
Why is it so important? So these provide, well, so science does a few different things, right? I mean, it's always nice when science gives us something completely new, something we didn't expect. But a lot of science is also, does this actually hold up things that we have predicted? Have we just been building castles in the sand, or is there actual experimental evidence that confirms why we think about things the way we do? And this is exactly that. This is something that we've been looking for. This is the second one, really. As you said, Einstein predicted it based on his equations. We expected them. And when we found them, it is really a solid confirmation that relativity isn't the whole picture. And we can maybe talk about that a little bit later, but at least on the realm we're talking about, it's quite accurate. This realm of extremely large distances, large objects, relativity is extremely accurate in modeling how these objects work, how they merge or orbit each other, and what signals we're going to get from that. Why else is it important? I would say it's probably also just important because it's nice to know. That's what science is about. Yeah.
Awesome. I've always wondered about this particular thing on the nature of mathematics. Would you lean more towards saying math is something natural, or is it something that we've invented?
I would definitely say that I think my answer to this question has changed many times over the years. Well, I would definitely say that, but that's not an answer. So I think there is some inherent... So what happens with maths, maybe let me try and describe a little bit about a few different mathematical structures, and maybe that'll give you an answer, or maybe that'll give a sense of why it's sort of both. So I mean, how did maths start? Maths started with counting. integer numbers, whole numbers, 1, 2, 3, 4. And then we obviously came up with addition, subtraction, later multiplication, division, that's all fine. 0 came along later, that's all good. So what do we have? But now we have things that are quite abstract and quite far removed, or they seem quite far removed. What's happened along the way is that we've seen these patterns and we've tried to take what's important about the underlying pattern and create and define an object that has that pattern, rather than specifically being this object. It's just any object that has this pattern. So, for example, a group is a set with an operation. So, for example, if you add two things, you should get another element of the set. And the integers, the whole numbers, are an example of a group under addition. But it's more, it's nice that we have the integers, but it's also important that we have this idea of a group. Now, did we invent this? In a sense, we put a name to a concept, but in a sense, it was already naturally there. And, it's not, so the rational numbers are a group, the real numbers are a group. It's not, so it's quite difficult to say, is what I would say that we put names to things that already exist in order to understand them better, I think is the best way I could put it. But I do
You're
think
saying like
that
categorization is basically what we've been doing and somehow just discovering that it exists.
I think fundamentally, I don't think we invent new mathematics in a way that someone couldn't reinvent, like in the sense, and I think this is well known, or maybe this is sort of an argument that I've seen before, that if we were to all be wiped out, tomorrow, and we lost all trace of maths and physics and science generally, you would get the same maths. Another civilization that came along later on, they couldn't have a different one. They can call it whatever they want. They might be the exact same as us and call 1, 2, and 2, 1. That doesn't matter. But the actual number can't change. And in the same way, the patterns that we've extracted and then, generalized, those can't change either. So that, in a sense, that's quite fundamental, and it's not really something that required us sitting around here to invent and think about.
You're saying the relationships have been predefined naturally, and we're just putting names to things.
Maybe predefined is its own theological question, but I would definitely say that they're natural, and whatever we discover is what we discover. But things that we invent, I think, it is difficult to say, because what is something that you invent? It's something that we create out of materials that already exist in the universe. It's not inconceivable that would exist somewhere else. So it's quite maybe on some level it's a bit of a semantical question too. But personally, I would say that we discover more than we invent.
All right, on that note, let's take a quick break and we'll be back right after it. What's up, everybody? Ron here. Just wanted to say a huge thank you for those of you who have listened so far. I really appreciate it. Hope you're learning a little. Before I go, I just want to say that today's episode is sponsored by nobody. Nobody's sponsoring us. With that, let's crack on with the rest of the show. Enjoy! Welcome back to the Tell Me series, a new podcast series with a goal to look outside our bubbles and rekindle our childlike curiosity about the world. Today, we're exploring the mysteries of mathematics, astrophysics, and music with one of my best friends, Varun Kumar. So, Varun, before we went on the break, we talked a bit about if mathematics was more nature or whether we invented it. Now, following up on that, would you say it's a universal language?
Yes, I think I maybe this is a bit of maths propaganda, but 100%. I think if you want to talk about things that connect everyone, there's other than artistic things are nice, and there is definitely there's a very nice human emotion to them, but maths. The power of maths, the power of the dark side, comes from the fact that it is exactly that. It is very good for expressing information that is maybe quite difficult to express in any other way in a manner that is precise and sort of unchanging, and can be communicated equally to everyone around the world.
So if I had to reframe the question in a bit, let's say, I guess this is more of a hypothesized viewpoint. If we had discovered aliens and we had to communicate with them, would you say math is our best bet?
Ooh, now that's quite I think that's actually quite a different question to me. And I would say I think maths is a good bet, but not the only thing. I think I would want us to try a few different things. But that's the thing. Maths is a language that conveys maybe not the right kind of information. You can't use maths to tell someone your name.
Mm-hmm.
And so you can tell them, you can use it to say, well, I weigh this much, but then you have to tell them what weight is. And so there needs to be some natural, actual communicative language that you use as well. I in fact, since you mentioned music, I think music would be the first, for me at least, the first avenue of communication with any foreign civilization or like alien civilization. Yeah, but I mean, they definitely would know maths if they had made it all the way over here. But,
I sure hope so.
I'll take a bet. If anyone who ever listens to this thinks that they won't, I'll happily take a bet with them.
All right.
Yeah.
Would you say, do you have a favorite mathematical sequence or theorem?
I think there's a few different ones I like. I like Fermat's last theorem. It's obviously quite famous. Well, maybe not obviously, but to a lot of people listening to this, to mathematicians.
What is it?
It's actually quite, good question, actually, because it is actually quite easy to explain. So for most people, I assume listening to this will have heard of Pythagoras' theorem, which discusses the sides of a right-angled triangle. And it basically says, for the two smaller sides, if you square them and add that, you get the square of the largest side.
Mm-hmm.
So as a mathematical statement, I might say a squared plus b squared equals c squared.
Yep.
And
good old high school.
Yeah, exactly. Yeah. Maybe even primary, actually. I don't remember. But anyway.
I don't know what you were doing in primary, but that was not what I was doing.
Okay, fair enough. So Fermat's last theorem is actually a slight generalization of this. Well, it seemed like a slight generalization. And what he did was he looked at the power. So in a squared plus b squared equals c squared, the power is 2 everywhere. And he said, okay, well, what if the power is n? We don't know what the power is. I want to talk about a to the n plus b to the n equals c to the n for all n. And he conjectured, and conjecture is the official word for, basically he guessed that, and he didn't guess without evidence. Like, let me say that. He did, so he proved this in the case of n equals 4, but he guessed that this would have no non-trivial solutions when n is greater than 3. So if I have a cubed plus b cubed equals c cubed, and none of them are 0, because then that's just the same number on both sides. That doesn't really count. Or if it's a to the 4 plus b to the 4 equals c to the 4, etc., then you won't have any solutions essentially. And so Pierre de Fermat was a French, he was officially a lawyer and a diplomat. Maths was like his side project.
Wow, side hustle.
No, for real, actually. So, I mean, this was actually a very small part of what he did. He invented probability as a side hustle. Imagine that. But anyway, so this was actually happening around the 1600s, and the full proof of Fermat's last theorem was, I think, done in the 1990s, but I think in 1995, maybe. I'm not sure about the exact year. And this was done mostly by Andrew Wiles, but obviously building along a lot of other work along the way. The full proof, I think, is 105 or something pages.
Wow.
And each page is sort of a mathematical paper in its own right kind of deal. Like, that's how much work went into this, just from him, but along the way, several new fields were invented. Many of these were connected across different areas that people thought had nothing to do with each other, specifically modular forms and elliptic curves. But I mean, I know that those, we're not going to get into that. But
So are you saying basically that through his theorem, most of the mathematicians today, or well, maybe not most, they're basically working on his homework that he didn't finish?
Yeah, well, sure.
Their entire careers are based on stuff he just invented.
Yeah, true. I mean, it that's a good way of looking at it. I mean, and that is the sort of interesting and fun and also slightly terrifying thing about maths, because you write down something that is quite innocent and looks like something that we've known for, at that point, maybe 1,000 or 2,000 years, which is Pythagoras' theorem, and you have no idea that it's going to take 300 years or some 350 years for people to actually solve it. I mean, it's just a weird thing. It looks almost exactly the same, and just shifting one thing can put you in a completely different zone of maths. Which is obviously the nice and the not so nice part, depending on how you want to look at it. But yeah, I'd say that's definitely a contender. It was one of the first. There's a book by Simon Singh. He's an author from the UK about this that I think is actually quite nice. It's much more historical. There is some maths in it, but it's a very nice book to read. I think you don't have to actually know a lot of maths to read it. So I would definitely, and he's written a few good books on other stuff we've talked about to do with physics, as well as some stuff on code breaking. So yeah, all of those books are excellent books, actually, for any kind of people interested in these topics.
Awesome. Appreciate the recommendations. Now, most people consider math and music to be on opposite sides of the spectrum, like math being very logic driven while music being very creative driven. However, both you and I understand that math and music have quite an intimate relationship. What are some direct parallels you see between the two?
I think, in fact, you've brought this up, and there's a lot of stuff. There's maybe the more common stuff, but actually, the first thing I want to talk about is something that you said, which is a misconception in maths, is that it's very logic driven and not very creative at all. Especially when you're at, I mean, I think there is a problem. I've seen a lot of memes around where people, basically teachers criticize students for not doing things their way, which is the right way. Mm-hmm. And that, that can be right and wrong depending on the situation. But I think that there isn't a lot of emphasis placed on creativity in mathematics in school, whereas you have to be creative as a mathematician, because everything you can immediately think of, someone else has already thought of. 100 other people, 1,000 other people have already thought of. Mm-hmm. It's not going to be new. You have to actually think of a creative way to actually, if you want to solve something new. So that's actually I would say not a whole lot that we do now is something that you just do by slogging, because we have computers for that. So the human element is actually the creativity bit in maths. So that's one thing. But definitely, so number theory is, I think, well, for people who maybe don't know and aren't really sure what number theory, sounds a bit fancy, but number theory is basically about integers and I mean whole numbers and how they kind of play nicely with each other. And I think that there is some kind of deep connection here between maths and music. So in music, we know about things like fifths and thirds, and so these prime numbers, but then there are these nice primes that sort of go together quite well in number theory and in music. And it's interesting because you can actually also track it in frequencies, because when you go up an octave, you've actually doubled the frequency. So I would definitely say that there is a factual relationship, but there's also, I think, for a lot of people who do maths, one of my course mates actually has done a music degree previously. Mm-hmm. So there's, I think, for a lot of people who do study maths, music is also an integral part of their lives. Did you catch that pun? Integral, because integers.
Got it.
Yeah.
Math nice. Jokes, the best.
Yeah. But Yeah, so music is definitely a big part of people's life. I mean, for mathematicians, a big part of their lives. I mean, famous mathematicians, Einstein, or physicists, Einstein also played like the violin, I think. Yeah, it's very common. I think it does, however, also exercise a slightly different part of your brain that I think doesn't maybe get exercised so exclusively when you're just sitting on and like looking at a page and doing calculations. So I think it is good to have a bit of a balance, but there is also some sort of transferable maybe understanding or like ability to kind of look at music and listen to it in a maybe analytical manner and maybe try and do the same thing when looking at maths.
So why
Yeah.
would you say that? I mean, from your experience, you've already mentioned that most musicians, or at least famous mathematicians in that sense, have had music as a part of their integral part of their lives. Um, I just wanted to ask you, why do you think that is? Is it something that comes from a personal standpoint, or perhaps it's cultural? Or is it just that most musicians or mathematicians are, more in tune with the other subject?
I think it's probably a bit of everything. I definitely think a lot of mathematicians, well, maybe they didn't start out very rich, but the most famous mathematicians were quite brilliant and therefore had permission to. They were given sort of grants to study and do their own thing and do their own time. And I think music is has been quite a natural hobby, therefore for people to go to. It's uh it's a bit less of a visual thing than like visual art, for example. And I think for people who spend a lot of time staring in quite an intense, concentrated manner at stuff, I think something auditory is a nice break, and that might be why there's maybe a tendency towards music instead of, let's say, painting. At least from what I've seen, I don't know. I mean, personally, I do actually prefer music to visual art because I'm better at one than the other. Um, but yeah,
Would you
I
say
think it could
music
be.
helps you concentrate more? Like we've often heard studies about people saying you should listen to classical music because it helps your focus. Is that true? And if so, have you ever done that while you were studying growing up?
Yes, I have. I think it's an interesting one. I think there are times where I think music will stop me from being at my maximum productivity, but if I am not feeling very productive, music will at least get me to like a minimal level of work done. And especially, so I have never really been big into classical music. I feel like when I try and listen to classical, I instinctively go into this mode of like, they're using this instrument here, or trying to think too much about the music. So personally, I prefer lo-fi hip hop, which has obviously become quite popular in the last couple of years. And I did use this and also Star Wars soundtracks when I was studying for my German exam. But I do find when I'm trying to do maths, actual hard maths, I'm actually trying to focus. Silence is the best. If I'm listening to music, I maybe it's just a me problem, but I enjoy music too much to actually try and concentrate enough on maths at that point.
I see.
So
That makes a
I
bit of
do know that
sense.
yeah, I know that it can be good for some people, but I think it's more good for, well, like when I say I was studying for my German exam, I mean specifically, doing vocab tests and just like relearning something quite mechanically. And in that sense, I think music can be good for making sure you don't get bored and stay on track and stuff. But when you're trying to actually think about actively quite hard about what you're doing, I think music can be a bit of a distraction.
I don't know if like your perspective is very different than what I've experienced at least. I don't really study with music, but when I try and at least when it comes to memorization, I use a lot of music to get those whatever words or formulas in my head. So for me, it would be either using mnemonics, like words that rhyme, words that sound
Yeah,
the
yeah.
same, or sometimes even making a beat, like having a specific like tapping rhythm to remember the amount of terms in an equation or something along those
Yeah,
lines.
I think. I mean, I've never tried to use music to remember anything in maths. I think that that might have been a good idea, but I think I would have found it quite difficult. I've never been much of a mnemonics person or something. I know that they are well known as like quite good as like memory, yeah, good for memory and stuff. But I don't know. I think when I'm trying to learn just vocab lists, just just again and again and again. The Indian method, just don't complicate the method. Just do a lot of hard work.
I see. But
Yeah,
I mean, we've had it
work
growing
hard,
up
not
a lot.
smart.
Work hard, not smart.
Yeah.
Interesting.
I mean, I know that that's definitely not what people say, but I found that app's worked for me more than anything else, because I think it's helped me then bring the individual words more easily to mind when I'm also out and about, in a natural, like speaking German. I actually have the word come to mind without having to do something specific, which I think I might have had to do had I tried to learn it in that way. For example, some people say you can chew gum, and then when on the test, if you chew the same gum, fine, but I'm not always going to have chewing gum on me, and I need the actual word in real life too. So
You're just saying your method's a bit more reliable.
I mean, it all depends what you want. If you're in school and you're forced to take a language class that you don't feel like you're ever going to use, and this is going to help you get through that test, do what you need to do, pass your test, and move on with your life. For me, in this situation, I actually am living in Germany and will ideally continue to live here. So I would want to learn the language in the broadest way possible, rather than in the quickest or most efficient way to pass the test possible. I mean, the test is fine, but it's more important to me to actually learn as much of the language as possible.
Right. So I think where you're coming from is, if you're looking for a quick fix, then all of these mnemonics or quick methods of memory help. But if you're looking for mastery, then you need to have solid fundamentals that don't really require.
I do. I don't know about other people. I mean, everyone's different. Everyone has different talents. This is just how it works for me. I know that when I learn things just for tests, I just, I'm there, I have it for the test, and then it's gone. Within like a week, I can't remember anything about it. And, which is fine, but that's not how I want to learn this language.
Makes sense. I think, from a very rudimentary perspective, we have used music to learn the basics, like our ABCs. Like nobody
of course.
thinks so. Every time I try and figure out where is L, I'm like, oh no, I need to sing the whole thing to figure it out.
Yeah. Well, and I know it's before M because of that.
Yeah. It's because there's you've in your head, you've paused, you've cut the song in half at that point.
Yeah, and it's we definitely, and music is a super useful tool for learning. I think so. I guess that was the other thing I was going to say. For languages, what I did use music for was I actually listened to German music, and that for me is something that I really connected with. So I've started recently, over the last couple of months, listening to a bit of German pop and quite relaxed, toned down stuff, not like intense rap, because what am I going to know? But yeah, so that's been quite good. And that stays in my mind a lot more than, an individual, like words for a word chart. So it is quite useful that way. I definitely agree.
All right. And before I get to our final question, are there any YouTube channels or books you'd recommend for all the people out there who are interested in learning a little bit more about math or astrophysics or music? I know you brought up a couple before, but feel free to add in a bit more if you want.
Yeah, so I think a couple of different ones. I mean, I think most people know about Veritasium, which I have been going through quite recently. I knew about for a while, but I've only started really watching intensely quite recently. Different people like different things. So I also, the other thing I like to watch is TED Ed, which has quite a wide range of topics, not maybe that many on these specific areas, but also quite a few on maths and astro. The other one I would say that often has quite interesting videos that they try and cater to a wide variety of audiences too is Quantum Magazine. So that's actually a channel, and if you watch, for example, their roundup of physics in 2020, and I think there's one for maths as well, and they just have some excellent videos. I just watched one, for example, yesterday or day before on the standard model of physics, of particle physics. And that's obviously the other half of physics. And when I said that relativity isn't the whole picture, that's the other part of the picture. And trying to connect them is what we are trying to do. But that was an excellent video and something that I think anyone could watch pretty much. It was with a very good introduction and quite a good level. So yeah, I'd say there's just a few out there if you like to watch Once in a while, I like to watch people actually solving some maths problems just to see how people are doing. Then there's a YouTube account called Flammable Maths, which I enjoy.
Sounds intense.
Yeah, he's quite memey. He's heavy on the memes, but he solves. And I think for me, it's just nice. Like you see a question and you're not really sure how it's gonna go, and then he goes a specific route. It's almost like watching someone do a puzzle solving, or like lockpicking lawyer. It's a bit like that. You're just watching someone do their thing, and it's quite interesting to watch. Anything on Astro specifically? Nothing's coming to mind. I haven't really watched that many of, for example, the Wired videos where it's like astrophysicist explains something in 5 levels. I imagine those would be quite good, but I haven't seen them.
All right. And the last question of the day is based on the theme of the show. Tell me. So I'd like you to tell us, with all of your experience in math, astrophysics, and music, what is one piece of advice or perhaps a piece of knowledge you'd like to leave us with?
Oh, the hardest question for last. Okay. I think I don't want to, maybe not advice. I think knowledge is probably what I would. Actually, I'm not sure. Advice is probably safest. Um, I would definitely say it's just to be interested. I think it's so easy when you're growing up in school. We don't. I think we really just don't realize where that is the only time where you can just learn. It's only expected of you that you learn. I think this is something that I actually got right in school, which I got a few things wrong in school, but this was one thing I really appreciated, that we had access to all these subjects, had access to teachers who knew a bit about these subjects, maybe not everything, but that's fine, enough to get us started. And I just really enjoyed learning about, as much as possible. I enjoyed learning history, I enjoyed learning geography and political stuff in MUN, languages. Um, yeah, so I think it's really that. Just be interested, and I know it can be difficult if you've had a subject or a teacher for a subject that has been quite bad, but there are better teachers out there. Of course, if anyone wants to find out more about maths, they can always just message me, and I'll happily, or Astro, and I will happily just talk their ear off about it. But yeah. Yeah, I mean, there's a lot to learn, and obviously, you can't learn everything, so pick what you like. But don't. I would encourage people not to think of knowledge or the idea of learning as boring, because I think that is something that schools, maybe the idea of going to school every day for the next for however many years. I think that sort of reinforces this thing of I can't believe I have to go to school again. Blah, da, da, da. And I think people find learning, or can tend to find learning, quite boring, and I would want people to not do that. Different presentation, different subject, whatever works, but keep learning. Learning is fun and good.
I think you said exactly what the point of this whole series is. The
Yeah,
idea is just to learn stuff, regardless of whether it will apply anywhere in your life, just
yeah.
because it's fun to learn.
It is
You
fun to
don't
learn.
need it for your job, you don't need it to get more money somehow. It's just about, hey, I don't know about this. Why not learn it? I mean,
Yeah, exactly. And yeah, I mean, I hope maybe if anyone does listen to this, I hope they've learned something. But
I mean,
but yeah, I think it's super important, and I'm a big fan of this podcast already, and I look forward to hearing the next few episodes.
awesome. Thank you so much, Varun, for being on our show, the first ever episode of the Tell Me series.
No worries, man. I'm very glad to have been here, and thank you very much for inviting me.
All right, catch you next time.